you'd like to follow along, I'm going to walk through cloning this repository. So this is the URL for this repository, Waterhackweek/waterstats. I'm going to copy the URL here for the repository. So this repository has 3 notebooks. The first one walks through a case of doing a hypothesis test with some streamflow data. The second one doing some linear regression with snow water equivalent from Snowpillow site. And then the last one is misspelled, but working with gridded data is actually the notebook from Tuesday that I didn't finish covering, and I thought this might be a good time to look at that and if folks want to play around with it. So here in our Jupyter Hub command line, just on the terminal, I'm in the directory where I want this to be downloaded. So I'm going to git clone and then paste in my repository name there, and then cd for change directory into waterstats. And if you have questions at like any time during this, just unmute yourself. Don't bother with Slack. We're a small enough group here. Actually, I can close out of this terminal tab and just go over in my directory here to the waterstats folder. And I'm going to open up the first notebook for hypothesis testing. Actually, I'll open up all 3. Just so I can close out of the sidebar here. And let me zoom in so this is easier for you all to see. So these notebooks are derived from course material for a class at UW in the civil engineering department, data analysis and water science. And then there's also this USGS publication, which they actually just released a new version of it this year, called Statistical Methods in Water Resources. It's sort of like the textbook for that course. It's super helpful, and in fact, the latest version of it, the 2020 version of it, has programming examples in R. So if you're an R user, that's fantastic because they have already got all these examples in there. But for Python, we can sort of adapt their examples as well. So the first thing I'm going to do here is import libraries we're going to be using to do some hypothesis testing with streamflow data. So we're going to use NumPy and Pandas that you've seen before this week. We're also going to use the SciPy stats library. This has a lot of statistical functions that are super handy that we can use. I believe NumPy and Pandas also have statistics functions built into them. But SciPy stats has a lot more. And in fact, a lot of other libraries like Xarray are actually have functions built on top of SciPy. I'm going to close out of my Slack because it keeps popping up. Don't ask me a question on Slack, just unmute yourself because it keeps popping up here. All right, so for this example, we're going to look at streamflow data from the Skykomish River here in Washington. If we look at the data, which we'll below shortly, it looks like there's a change in the peak annual streamflow around 1970. First, we're going to load in our streamflow data. So there's this Excel file included in the repository if you've cloned this. And there's actually a Pandas function specific for reading Excel files because there's different metadata and stuff embedded in them other than just like a normal plain text CSV file. So we can read in our Skykomish data file, which we give it the path here. And then we can use the head function to just look at the top 3 rows. We're saying head, the 3. And so that's just going to print out our first 3 rows. So we can see the contents of this file. We have the date of peak flow, the water year, the peak flow value, this is in cubic feet per second, because this is USGS data, and gauge height in feet. which if you really want, we can convert these, but we're going to work in the imperial units here. So we can plot this saying, using the Pandas plotting function, which really is a wrapper around matplotlib, where we can say Skycomish data plot X, we want to put our water year, Y, we're going to put our peak value. So here's our time series. And we're guessing, we're kind of hypothesizing that around 1970, something changed here. So that's what we want to test. And in fact, specifically, our question is, with this time series for the Skycomish River, we're thinking that there was actually an increase in peak flows. I don't know, if we squint at it, you could maybe say after 1970, there's some increase in peak flows. It seems like our top values are more after 1970. So we want to test the statistical significance of the observed change in the mean peak flow before and after 1970. So in other words, how likely is it that the mean peak flow before 1970 comes from the same sort of overall distribution as the mean peak flow after 1970? So to start, we're going to split our data into two groups. So we're going to have before and after 1970. And here I'm using an index notation where this is gives us a true-false array. So we're saying water year is less than 1970, we'll have true and false values. And then here, greater than or equal to 1970, true and false values. And then that lets us just select wherever those values are true from our original data. So if we run this, and then we run our Skycomish after 1970 series, look at the first few values, we can see that those indeed start at the year 1970 and go on. We can just plot these again, but now we have it separated in two chunks, so I'm just plotting them separately, or plotting them together, but with different colors and stuff. So we can see that we've divided these up. A good thing to do would just be to check a histogram of both of these data sets to see, what does the distribution of these look like? Does this maybe help us get a better idea of what kind of changes we're looking at? So matplotlib actually has a histogram function where you can give it values and then the number of bins that you want. So we're just using that here since all we want to do is plot that. We're not going to do any analysis with the actual histogram. So here we have a histogram for before 1970, after 1970. And maybe if we squint at that, you could say, oh yeah, it sort of looks like after 1970, there's like an increase. Looks like the peak of this distribution shifted. So what kind of hypothesis test should we use here? Well, let's consult the experts because we're not statisticians, but we can read a book, Statistical Methods and Water Resources. This figure isn't displaying. But I can actually go to the book because I really like that figure, or it's a table. There's a link to that book at the top of the notebook. There's a PDF of it here. So I reference this often because there's a table that kind of tells you, or gives you an idea of what sort of hypothesis tests you want to be using for different types of data. I happen to know that it's on page 97. I also happen to know that it's on page 105 in the 2002 edition of this. That's how often I reference this. So here's our table. It's asking us if we have parametric, such as like scalar data, which we have, or non-parametric, such as categorical data. And then each of these rows, is kind of like what type of data do you have that you're comparing? And there's actually like the whole chapter about these different types of tests. So what do we have? Parametric data, because we're looking at scalar stream flows. And this first row, 2 independent data groups. Well, that's pretty much what we have. We've separated our streamflow data into before and after when we think there was some sort of change. And so if we go to chapter 5, we can find, it talks about this 2-sample t-test. However, I'm going to deviate from this a little bit. It says we should use a t-test, but if you read in chapter 5, it talks about how the t-test is where you can assume the standard deviation of the two sets are the same. However, we're not going to do that. We're going to use the standard deviation of the data we have. And so that variant is actually called a z-test. I have links here to Wikipedia, which honestly is a pretty good resource for this sort of information. And so we're going to go ahead with this variant of the t-test, the z-test. And the first thing we want to do is state our null hypothesis and our alternative hypothesis. So when we do the statistical test, what we're actually doing is setting out to see if our null hypothesis is supported or not. So our null hypothesis here is that the peak flows of the early period are coming from the same distribution as the peak flows of the later period, that there's no change. So we can say here is our mean of early is equal to the mean of late for those distributions they're coming from. Our alternative hypothesis is that the mean of the distribution of the later period is greater than that of the earlier period, coming from a different distribution. This is a one-sided test because we're only testing for a change in one direction. It would be two-sided if we said our alternative hypothesis is that it's either greater or that it's less than. But here we kind of are guessing that it looks like it's changing and going to a greater peak flow. So we're going to use a one-sided test. This is the function that actually computes the z-test value. You can, so the means of the two periods and then the standard deviation, which is actually a pooled standard deviation value. So it's a function of both the standard deviations of the early period and late period, which we'll see below. The z-test uses a normal distribution, which I've plotted here. Just a normal distribution, and I've selected an alpha value, which defines our confidence level. So if we want to have a confidence of 90%, our alpha value, it's actually wrong, this is confidence, not alpha is 0.9. So our alpha is 0.1 and our confidence is 1 minus the alpha. So our confidence is 0.9 or 90%. So essentially what we're going to be testing is we assume we have some distribution that the early period mean is drawn from. When we compute the z-test value, if that value falls anywhere within this distribution below this red shaded in area, then we cannot reject the null hypothesis, which means that there has not been a change. We have to accept the null hypothesis that they are coming from the same distribution. However, if our z-test value falls in this red shaded area, then we can reject the null hypothesis and say that there has been a change. But note that this is all dependent on the confidence level we have. Yeah, is there a question?
I'll use that pause just to say I'm so sorry. I got wrapped up into answering questions on Slack.
Okay, no worries. If there's no question, I will move forward. So we can change our confidence interval here and say, you know, if we want to use 95%, what essentially that does is that shrinks our region down here. So we are, you could think of it like we're less likely to actually reject our null hypothesis and less likely to say that the peak stream flow has actually changed. And that depends on what the confidence level we want to set. And so we'll see that below, what happens when we choose different confidence levels. We also want to make sure we have a large enough sample size. So a sample size at least greater than 30 is recommended by the smart statisticians who develop these methods. And we have that. We have 41 and 40 for our two before and after periods. And so now we can pick a confidence level that we want to test this at. So let's say we're going to use an alpha of 0.05 our confidence is 1 minus the alpha. So our confidence is 0.95 or 95%. And then our null hypothesis is that there's no change occurring. And so there's this delta factor, which could, if we wanted to say that our null hypothesis was that there is a change, we could change this, but it's 0, so it's actually not going to factor into our equation. So first, we want to determine what the z alpha value is. So that's the z value, or the value on the distribution that corresponds with our confidence interval, or our confidence that we chose, which is actually where this red shaded area stops. That's the z alpha value. It defines that cutoff point. So the SciPy statistics package lets you look up from a normal distribution the confidence level. So we just say, we're just passing the 0.95 value to this normal distribution, and it's going to return our z value. Now the z value is just the value along the x-axis here. So now we can compute the z-test value and also a p-value to look at the result of this with the 95% that we chose. So first, we're going to grab the mean of our two data sets before and after 1970, the standard deviation of those, compute the pooled standard deviation, and then finally the z-test value, which is just this equation up here, and print out the result of those. So we get a z-test 2.16, a p-value 0.015. What exactly does that mean? I think it's best to visualize this so that our z-test value does not exceed the z-alpha value, meaning that with 95% confidence, there is a statistically significant, did I say does not? It does exceed the z-alpha value. So there was a statistically significant change in peak flow around 1970. And the p-value is telling us that we could go down to an alpha of 0.015 before we can no longer say this is statistically significant. So, and that alpha corresponds with a 98.5% confidence. Visualizing this, just like on the plot above, we can just plot a vertical line where a z-test value fell, and it did fall in that rejection region where we can reject the null hypothesis that there was no change, which means we can accept that there was a change. But what happens if we tried it with a 99% confidence interval? We can run the same thing and plot the results, and we can see that our z-test value didn't change because we're still working with the same data here. What changed was our z-alpha region, which shrank, and now we're falling on the left side of that. So with 99% confidence, we have to accept the null hypothesis that there was no change in the peak streamflow. So this is just one hypothesis testing method. I really recommend this book. It's so helpful, and I've been like referencing this book all throughout graduate school so far, and I still haven't even got through everything. And now they have a new version of it out. Before I move on to another notebook, I'd be happy to take any questions.
All I have to say is that I want to learn everything from you, Stephen. You're awesome, so thank you.
Thanks. Honestly, a lot of this is like, I don't fully understand all the statistics behind it, or like why certain statistical tests are recommended for certain types of data. But I trust that the statisticians that came up with those things did their homework. And so I'm just listening to what they say.
I just really appreciate all the commenting in your notebooks. I think that that's the big thing for me, is it's very, very clear. So thank you for that.
Oh, glad to hear.
I'll second that comment. Thank you.
Thanks. We can just move on to the next example, which is doing some linear regression, again with the SciPy package. And so here we're going to load in some snow water equivalent. I'm going to clear all my cells. So these snow pillows, they measure snow water equivalent, like at snow tell sites, measuring the mass of the snow and depth. So we can see this CSV file here. If we look at the first 3 rows, it gives us a year. And then I guess this was maximum SWE at these 2 sites. So this is Blue Canyon and Slide Canyon. I think they're snow tell sites. And we can plot this data here from our Pandas data frame and see what these 2 look like. And so the idea here is, you know, what if we had to remove one of the snow pillows? Like what if we had to remove Blue Canyon? We no longer have data there. Could we develop a relationship between snow water equivalent measured at Slide Canyon and Blue Canyon based on this data, so that we could predict snow water equivalent at Blue Canyon in the future, even if there's no snow pillow there? So that's what we'll be sort of trying to do here. And the first step for any sort of regression or correlation is we just want to plot a scatter plot and see what this data looks like. All right, that looks pretty bad. Like I can maybe convince myself I could draw a straight line through that. It's not the best data set to show in an example like this, but we can work with it anyway and see what we can do. Also, SAT vocabulary word of the day, heteroskedasticity, describes the, is the word that describes this sort of spread. So if you want to impress your friends with fancy vocabulary, that's the only reason why I know that word. There's a Wikipedia article about it. Because that's actually one of the rules. If you have heteroskedastic data, you should probably not use a linear regression on it, but we're going to do that anyway. We're going to be rebels and break the rules. The function we're going to use from the SciPy library is the linregress function. We can look at its documentation here. So we need to give it x values and y values, and it will give us a slope, an intercept, an R value, a P value, and the standard error. And we'll go into what each of those are going to be telling us just below. So let's go ahead and use this function. So we're going to say st.linregress. We're going to use our Slide Canyon values, the x as x, and then the Blue Canyon as y. So we're going to be hopefully try to be able to predict our y values using our x values based off this model. And we can plot the result. So we're going to do our same scatter plot as before, but this time we're going to plot a regression line. So for that, I create some x values, and I'm basing these off of the Slide Canyon values. So I just create a data set that has the same values as Slide Canyon, but linearly spaced, and then compute the y values using the slope and intercept from the linear regression we just computed. So yeah, there's our regression line. I mean, that's about what I would have drawn maybe by eye. It still doesn't look great, but what else did this linregress function give us? It gives us an R value, and from that we can compute an R squared. And you can see that these are pretty low, which is sort of to be expected based on what we're seeing here. It also gave us a p-value. So this linregress function actually does a statistical test behind the scenes. It uses a Wald test, which uses the t-distribution, and it does a two-sided test to determine if there's a statistically significant difference between the slope of our linear regression and a slope of 0. So essentially, is this would be useful for like a trend, maybe. I actually don't know examples of like where the wall test is typically used. It's not in that water science statistics book from the USGS. So just with these functions, be careful using like the defaults, because this may not be appropriate for your data set, but we can look at the p-value anyway. And like, okay, like our p-value is really low, so we can say with high confidence it's not a slope of 0, but that's not really what we're interested in here. It's just interesting. And then finally, we get our standard error from our linear regression here. So after doing a linear regression, we also want to look at our residuals. So we can compute that here and just say, you know, we have our observations of Blue Canyon minus the predicted values from the linear regression, and then plot a histogram and a time series of those residuals. Typically, we want our residuals to be normally distributed. This histogram looks sort of normal, although it's biased low, maybe. And then we also don't want to see any like trends or patterns in our residuals over time. This looks fine, I guess. It's like super noisy, but it's not like sloping up, or it doesn't have some like sinusoidal pattern, because that would imply that there's some other underlying pattern that we're not capturing with just a linear regression. But here, I think it's just a bad fit, but it looks like random noise, so we can go ahead. So now we can finally use our linear model to make predictions. So we can pretend like we have no measurements at Blue Canyon. And so we have to use the X values from Slide Canyon times the slope plus the intercept from our linear model to get Blue Canyon predictions. And then we can plot that together with our true data. So in black here are the predictions for Blue Canyon based on the blue line here, Slide Canyon observations, using our linear model. It doesn't match, it maybe matches like in 1 or 2 points exactly. It gets the magnitude right. Like it obviously tells us that the magnitude of snow water equivalent at Blue Canyon is much lower than at Slide Canyon. But this is sort of a poor model, but it's an example of using a linear regression to make some sort of prediction. And that's it for this notebook. I can also take questions about this. The last notebook I have is actually from the Tuesday tutorial. It's the notebook I didn't get to, and I added a linear regression to the end of this. If you want to work through this, I don't know how much time we have left. Am I supposed to go?
I think we have a lot of time.
Okay.
I believe not only does this go till, well, nominally 10 more minutes, in that the official break is 15 minutes. In practice, I don't think we have anything officially scheduled for, or any floating tutorials for the 11 a.m. Session.
Oh, okay.
But anyways, there's at least 10 minutes. So
I'll go through this notebook then, since I didn't have time on Tuesday, and I tried to connect it with the
that's sneaky of you.
stuff here. Yeah. I like the plots in this notebook. So if you remember on Tuesday, I was looking at Mount Rainier with DayMet. I was looking at snow water equivalent because Mount Rainier looks cool when you look at it on a map. So here we're gonna load DayMet data again from the OpenDAP endpoint that is provided. We're going to look at just the area around Mount Rainier and try to answer the question, how is April 1st snow water equivalent around Mount Rainier changed in the past 40 years? 40 years being the record that DayMet can give us. So to start off, we import our libraries here using Xarray to read in our data, GeoPandas, and some other PyProj Shapely geometry libraries to work with our geospatial data to do some of the subsetting, and then SciPy Matplotlib. So we can open our data set here and get our coordinate reference system that's used by DayMet, that Lambert conformal conic system, and then define a bounding box that we want to clip our data to. So this, I went on Google Earth and just found some points around Mount Rainier. And so we can select from this just around Mount Rainier. Here, I'm probably not being super data efficient like Amelia was, because I went ahead and selected every variable instead of just selecting snow water equivalent, but we've only selected 48 by 60. I don't know, it's a long time series though. Go ahead here.
In your defense, that request that you have in there doesn't pull any data. It's just,
okay.
So you're fine. It's only when you do a plot or a data extraction that you actually pull data.
Oh, that's good to know. So here, I guess I just pulled in 1 day of data. So the first.
That's why it was so fast.
Cool. That is good to know. So this is what our snow water equivalent plots look like around Mount Rainier. It's a big mountain with a lot of snow on it. But we only want to look at values for April 1st. There might be a better method to do this, but this is what I came up with using a combination of true and false arrays to select where our time month is the 4th month. And we can use the AND operator to combine that with a time day is the 1st day. These give us just arrays of true and false values, but when we use them in the Xarray select statement, we can then grab everything that it corresponds to a true value and get rid of everything that corresponds to false. So what happens when we started off with this, what is it, like 14,000 time series, 14,600 days, and now we're just down to 40 days. So we just have 40 years of April 1st data. Now we can plot snow water equivalent for each of these days. And Xarray has some cool plotting features, such as I'm specifying my data set is my April 1st data set. And then the data array that I want is SWE plot. I give it my X and Y. I want it to do it on longitude and latitude. But then I can also provide a column and say, I want to essentially separate them out by time. And I can then say call wrap and say 6. So what that's going to do is for every one of the 40 time steps I have, it's going to make a plot. And then after 6 of them, it's going to wrap around and keep plotting. So this is going to make 40 subplots. And it takes a while, I guess, because I'm now pulling a little bit more data. So here we go. We have the titles are automatically set here for each year, April 1st, and we have our maps of snow water equivalent. So we can see there's quite a bit of variation. Some years there's really nothing. 2015, that was a low snow year. We can compute summary statistics for the whole data set. So we can just say, our data set name, data array, mean, standard deviation, min, or max. And this will just give us a single value. So this is computing the mean across space and time. But if we want to compute the mean across time only, and maintain our spatial dimensions, we can tell it in the mean function or method here, we can specify the time dimension. And you can see that we've retained our X and Y coordinates here. And if we plot that, we get a map of mean April 1st snow water equivalent for 40 years. Similarly, and maybe more towards the question we want to ask, is if we just take a mean across the spatial dimensions and preserve the time dimension. So here we specify a list of the dimensions that we want to take the mean across, X and Y. And we can see that that gives us 40 value, or still in the time dimension, 40. And if we plot this, we get a time series of our mean April 1st SWE for this whole region. So now tying it into the statistics, you know, if we want to say, is there a trend here? There are a ton of caveats, being that DayMet is this interpolated data set. It has a maximum SWE value. So like the glaciers on top of Mount Rainier are actually not really represented properly. There's a whole lot of things here where you probably wouldn't actually trust the results of this just based on the data source alone. And the fact that, you know, how representative is April 1st SWE of greater climate trends, I don't know, but we can do it for an example anyway. And here, in addition to doing the normal, or what I showed previously, the SciPy statistics linear regression, I'm also going to show another test, which is the Theosan Slope. And this one similarly gives us a regression line. It gives us some bounds as well. And we can provide it with an alpha value to do its tests. You can read more about it here. I don't know a ton about that method, but it is mentioned in chapter 12 of Statistical Methods in Water Resources. The USGS should pay me for advertising their book. It's a free book though, it's just a PDF. So we can run these tests and then plot them both on top of our time series. They look actually pretty parallel. They're shifted a little bit from each other, the Theosan and linear regression. That's sort of interesting. I'm not sure what what conclusion could be drawn from that, except that it's important to know exactly what statistical method you're choosing when you do some sort of test. Here it looks like they'd probably give you the same answer in terms of slope. So similarly, the way we pulled out a time series of mean and also got a map of the mean snow water equivalent, we can do something like get a map of the standard deviation over the time dimension and preserve our spatial dimensions. So this would be like if our question was, over the past 40 years, what parts of Mount Rainier have the most variable April 1st SWE? And so here we're doing our April 1st data set, the SWE data array, and computing standard deviation in the across the time dimension rather than spatial, and then plotting that. So this is kind of neat. So it's showing us here that there's more variation sort of on the mid slopes around the mountain. The top of the mountain has pretty much zero variation. But again, this is, I think, more of an artifact of the data set in that SWE reaches a maximum. And so it's not really representing snow on top of the glaciers probably. And then it goes down to zero in these areas where they're probably not receiving seasonal snow typically, or if they do, it's very little. It doesn't vary very much. Oh, and then I forgot, there's another bonus of plotting Landsat imagery with X-ray, which I don't do any statistics with this.